I have come across some surplus. These are temperature compensated crystal oscillators for 10 MHz. And I have quite a lot of them. These are available on the internet from various sources, including eBay, and they are not expensive. The output is a square wave of about 2 volts. The sideband noise is fairly high. I can see with Linrad within a minute or two, with very good statistics, you can see the imaginary part is well below the yellow trace. So at 0.5 Hz, I can read 88 dBc per Hertz. At 1 Hz, I cannot see something because that's the offset from 10 MHz. And then there are the overtones on the audio side, so Linrad is not suited for measuring at very close spacings. And further, there could be a phase shift because of the DC blocking. The sound card is not DC coupled. But at higher offsets, let's say 100 Hz, I see minus 136 dBc per Hertz. And I have been running also the PN2060, but that is very slow because of the large transform size. So I have to wait quite some time. Well, I can see 100 Hz, it gives me 148. But I saw here with Linrad 136. That's odd. The phase noise is not particularly good. You can see here. And the markers are well on the curve, except for at 100 Hz, where the result is slightly better than indicated by the table. So at 1 Hz, it is about minus 98 dBc per Hertz, but it is only 4 averages so far. So nearly minus 100. I guess this oscillator is designed for long time stability and not for particularly low phase noise close to the carrier. It's also designed, of course, for small size and low power consumption. So it's completely opposite from what I am working at. Inside the oscillators, there are this kind of crystals. They are third overtone crystals at 10 MHz. Very good ones. I have connected 20 crystals in parallel. Here is the thermostat. I will first find the optimum value of the thermostat control voltage, the setting of this potentiometer. To that end, I used a network analyzer with this very simple configuration. Weak coupling to the crystal package. Here is what I see at room temperature. Q is 1.146 million and the frequency is 4 Hz below 10 MHz. Here is the offset frequency as a function of the thermostat control voltage. And the flat region from here to here, 177 Hz, comes at 3.35 volts for the center. I don't know, of course, whether the curve is something like this or something like that, or maybe something in between, which would be absolutely flat here at the center. The resolution of the network analyzer is 1 Hz. I can look at this more in detail when the unit is an oscillator, because then I have very many decimals on the frequency, limited only by the phase noise. That frequency isn't absolutely constant. Now I have set 3.35, which should be at the center of the flat region. And I have waited long enough to have a stable situation. And now I can see that Q, which was 1.146, is now 1.115. So I have lost a little on Q. This could be because the frequency is much higher now. I will bring the frequency down to 13 Hz above 10 MHz, because that's the frequency of my Wenzel oscillator. I have added about 230 PF across the crystals to get the frequency 13 Hz above 10 MHz as I wanted. An interesting thing is that Q has gone up. It is now 1.198. That means 1.2 million. My Wenzel oscillator delivers 2.7 volts peak to peak, and that is in 50 ohms. 2.7 volts in 50 ohms, that's 18 milliwatts. And what I want is 18 milliwatts at 50 ohms. And that should be on the signal of the crystal. So it means I see the resistor R1 and the impedance of the crystal R2. And I want 2 milliwatts here, because 100 microwatts for each crystal. And I want 16 milliwatt, means the rest of the 18 in this resistor. So I do some standard computations. I want these two in parallel to be 50 ohms. And then I know that the voltage U squared divided by R is the power. So one is 16 and the other is 2. 16 and 2 milliwatts. So I find that R2 is 8 times R1. And I plug that into this. And I find R1 is 56 ohms and R2 is 450 ohms. I have arranged the crystal filter like this. First 56 ohms to make the impedance 56 ohms when the crystal is not loading. The other things are reactive only. Then a coil and a trimmer to set the imaginary part 0 here, so it is 56 ohms resistive. Then a capacitive voltage divider with 47 PF and this trimmer, and then a 47 PF up to the crystal. This is to provide the desired degree of coupling, means how much will the load be here from the crystal. And then the crystal is tuned with the main tuning capacitor and 200 PF in parallel. That gives the high impedance point on top of the crystals. And as a first test, I put 1.5 PF here, not to load this with the 50 ohm input of the network analyzer that I will connect here. The Q of the crystal will be slightly degraded because these impedances, together 25 ohms or a little bit more, is coupled to the crystal and provides some impedance at this point that will load the crystal. So Q will be a little bit less than 1.2 million. When I look at transmission, I see that the frequency is what I want. That means 13 Hz above 10 MHz. And Q is 1.14 million. So the loss is there, but not very big. The impedance at the maximum is 50 ohms, as desired. When I span a wider bandwidth, I can see what the impedance is off resonance. And you can see 56 ohms on one side and on the other side 56 ohms also. But spanning such a wide range, 2 kHz, doesn't give a reasonable result for the center. Well, 50 ohms. But you can see it is a little bit ugly. But this is what I wanted. Next step is to add a high impedance amplifier. I have connected the oscilloscope probe directly on the crystals. As you can see, I have lost about half a dB in signal level. The frequency has changed a little, but the effect of the probe is small, so I can look at the voltage just by putting the Wenzel oscillator on the input. Here is the signal level on the crystals, 2.82 volts. With 680 ohms in parallel with the crystals, I lose 6 decibels, means that the output impedance is 680 ohms. With 680 ohms in parallel with the crystals, I lose 6 decibels, means that the output impedance is 680 ohms. I have added a source follower with the J310, and then I take the output directly from the source into a 50 ohm low noise amplifier. And then I listen with the passive receiver on this. I had to add an inductor to provide DC for the base. And then I had to increase this capacitor to 220 pf to come within tuning range for the main tuning. This is only 30 pf, this trimmer. The voltage across the crystal was 2.82 volts peak to peak. That's the unloaded voltage. And with an impedance of 680 ohms, it would be 0.5 volts RMS in a 680 ohm load, which means the power into a matched load would be 0.37 millivolts. Now, the 680 ohm resistor, which corresponds to the crystal at the resonance frequency, is minus 174 dBm if it were a room temperature resistor. Now it is about 80 degrees, so it is minus 173 0.6 dBm. And that means I should see a signal-to-noise ratio very close to the carrier, which is 4 dB below 173.6, means minus 169.6 dBm. I will check whether that is what I observe when I try to measure it. I have attenuated the signal from the Wenzel oscillator by 100 decibels. And I have adjusted the S meter to show minus 100 dB for the carrier. That's S, minus 100. And then I switch off the Wenzel oscillator. It will take quite some time before it switches off, because I have very big capacitors to filter the voltage. You can see it starts to drift away slowly. Now you can see it stopped there. And now we see the thermal noise at the center of the filter. Or at least that's the noise from the crystal in its 680 ohm impedance. And I guess it is thermal noise. And the level, I cannot see the trace, but I can read the level anyway. And it says minus 170.9. I had expected 169.6. So it's a difference of 1.3 decibels. I don't know why, but it's fairly small, so I think this is okay. The problem here is very clearly visible now, when it has been running for quite some time, overnight that is. So I compare it with my old result, and it's really different. And now I know what the problem is. Here is what I see in Linrad when I look at the Allen variation. And you can see here I have glitches, some kind of interference, fairly narrow, close to the carrier, but strong. Here is what happens when there is such a glitch. And you can see it here. This is 20 minutes at reduced power. The power reduction is 10 decibels. And there has been no glitches in this time period. And then when I look at the PM2060, I see that at 10 Hertz the noise is something like minus 148, but it hasn't converged yet. This is about 40 minutes, still no glitches here. And sideband noise at 10 Hertz has decreased a little more, maybe 149. And it's still 10 decibels signal level below full level. And the wide range noise floor has not been correctly evaluated yet. There are circles all the way here. So the wide range noise is below minus 180 dBc per Hertz. When I compare with the result from the 3 crystal oscillator, nerds106, it looks like this. One more hour has elapsed, and just recently there was a big glitch. You can see the white here and red this way. So this is a strong impulse of some kind. And I look at here, it didn't affect phase noise much. That's interesting. It is approaching 150. It should go down a little bit below that even. Here is the 3 crystal experiment, the best I have had so far. But what I have now, here, particularly in this range, there is a problem. And that's probably this glitch. I will go back to the full power to see if glitches are more frequent, because I have a suspicion that they are generated by the crystals. Some micro cracks in the quartz happens, not very often, but there are 20 crystals in parallel, so if one of them makes something, the probability is 20 times higher than normal. This is what happens when I switch on 10 decibels more signal. This is 1 hour, and I cannot see the wide range noise floor yet, but there has been no glitches, so this is a valid result. There is still a noise problem here, or worst somewhere here, 4 or 5 dB. And I compare with that old 3 crystal measurement. The output is from the source follower, but I have loaded it with a resistor. That is this attenuator set to 5 decibels. This gives me perfect 50 ohm match, which makes the measurement reliable even at very low signal levels. I have replaced the source follower, the J310. The current in the old one was 1.258 milliamps. The new one takes 1.527 milliamps, and it is with the same source resistor. I have sorted all my J310 in order of increasing current when running with a grounded base and a fixed source resistor. And when I compare with the previous FET, first I make sure there have been no glitches, and then I compare with the old transistor, and here is the new one. It's hard to say, but it actually looks like the old one is 1 or 2 decibels more noisy. But here the difference is much bigger. The old one and the new one. I have reduced the source resistor from 180 ohms to 90 ohms. This has changed the output impedance from 113 to 83 ohms, although that isn't a fair measurement because the impedance changes with the signal level. The current has gone up from 8.5 milliamps to 12 milliamps when at full signal level, and the signal output from the box has increased by 2 decibels. Already after 15 minutes, it seems like this has been a small improvement. Here is what I have now, and here is what with the old source resistor. But at the wide range, the old looks better, but that's because the improved statistics. All the points here are marked with circles, and it's the same here, which means that the imaginary part is equally strong as the real part. Much longer times are needed, longer than 1 hour. I will leave this running until tomorrow because it's late now and I go to bed. Running overnight seems to have been successful. When I look here from 23 up to 8, there have been no glitches, and I don't think there has been one in the beginning either. So here is what I have observed now, and here is before I changed the current. We can compare, for example, here where there were the biggest difference. And I think this is just because of the better statistics. If you compare here, where the noise comes from the Wenzel oscillator, essentially, the difference is the same as here. But when I look here at 1 kilohertz and above, the imaginary part is still negative, and the value I see is minus 193 or so. This could be because of the output impedance. I have set it with the network analyzer, but I think it changes when the power changes because the current through the transistor changes. And if I look at the value, minus 194, for a signal of 10 dBm, that is 10 dB below the noise floor, and I don't think this is correct. I have to wait for the wide range noise floor until I have added another amplifier which has a proper constant output impedance. I have changed the operating conditions for the source follower by placing about 5 volts on the gate and a bigger resistor on the source. That gives me the same current and a little lower drain source voltage. And this is what I see, and this is what I had before with the grounded gate. And there are some differences that I don't understand. The imaginary part here is lower as compared to here, which means that the curve is noisier also. And this is 37 averages, and this is 37. It's the same time, about 1 hour. But there is no significant improvement. It looks like the same. And the signal level here is also very similar. And the frequency 12.924 or 925 Hertz. So it's 1 millihertz frequency difference. So this did not improve significantly. And here is some odd phenomenon, maybe related to the output impedance. And there are no significant glitches, but there is some small phenomenon I can see here. This means there have been some small amplitude changes, because this is the zero frequency, 10.000, where this is a phenomenon in the sound card, how it adapts to the DC component. Now some more time has elapsed. I'm still using a bigger source resistor and some bias on the gates. And this is the situation right now. And here is what I had before on the same configuration. Just better statistics. When I look at the Allen deviation, I see there was a major event here around 2 hours after starting. So that degrades a little bit the recording I have here, and I can compare it with what I had before with the same configuration but shorter measurement time. So I haven't really observed anything important now. I'm just testing various possible configuration changes. Here I have 2 source followers in parallel. Both have an elevated gate at about 5 volts and 330 ohms in source resistors for each one. And what I see is interesting. Here, if I compare with a previous result, the one with a single transistor, which is much better here, but at this point the difference is much smaller. So here is flicker noise from the 2 transistors, and I check here to see that there was no glitches or any other such problem during this measurement. I have decoupled the common DC biasing to the 2 source followers, and that made no difference. It is like before when I compare with the old result with only one transistor. I will try to go back to that particular first transistor to see whether it is still like this. And I have verified that there were no glitches this time. I have restored exactly the same configuration as I had before here, but a little more time. Now I have 37 averages here. That was the old result, but now I have 99, so statistics is much better. And the difference, it looks like a small improvement, but I do have the same circuit diagram as I had in the old, which was here. And I can't explain exactly why it looks better, but maybe it's just statistics. I now have two source followers in parallel. This time it looks okay. I think the problem was that I had VHF oscillations, and I made some little provisions to prevent that. So what I have now, as compared to with a single, the same transistor, this looks significantly better than that old. And I have to wait quite some time to get a correct measurement here because I have circles on the data points. And further, this is below minus 150 probably, and that's below the self-correlation of the PN2060. So I will have to wait for some time to see how this develops. During this measurement I had some events with glitches, this one and some other things. I think this has to do with crystal aging, but I'm not sure. The dual source followers have been running overnight, and statistics is pretty good now. And I can compare with the previous result with just one of these. Looks like this. And it is clearly a little better. And of course here much better. But it has not converged yet. You can see all the circles all the way here. So I have reached the specifications of the PN2060. I will attenuate the signal to see what happens then. During this measurement there have been two glitches, here and here. And these things, that's another phenomenon that I accidentally discovered what it is. When I edited the previous section of this video, I found this. You can see there is a big signal in one channel, in channel 1. And that causes these phenomena. So that is a system error, my measurement system that has some problem. I do not think that contributes to the phase noise. So now I know that these things are probably a problem in channel 1. It could be the sound card itself also. But I had a problem with the mixer in the I channel of channel 1, and I had to replace the Schottky mixer because it had become noisy. And then while searching for the problem I was disconnecting and connecting the BNC connectors several times. So I may have to do a major cleaning operation in the I channel of channel 1. I have attenuated the signal from the Wenzel oscillator by 6 decibels and also reduced attenuation into the PN2060 by 6 decibels to restore the same signal level, at least approximately. And here is what the result looks like. And here is what I saw at the full signal level, not overnight, but the first hour or so. And as you can see, at 10 Hertz, there is not much difference. At 100 Hertz, looks very much the same. So, well, I don't know exactly what to say, but it seems perhaps the performance I see here is the performance of the PN2060 and not of the signal I get through the selective amplifier. I have replaced the Wenzel oscillator with my old channel 1 oscillator. The frequency is a little higher, and I cannot make it higher than this because then I cannot tune my filter. I have removed the small capacitors and I have 200 PF now in parallel with the trimmer. The frequency offset is nearly 20 Hertz, so I can see 10 Hertz quite well. And the level I see here is minus 146.5. And that's surprisingly much noise. I can look at the PN2060 that has been running at the same time. And at 10 Hertz here I see minus 145.6. So they agree nicely. What is not so nice is that the noise floor at wide separation is much higher now. And that's peculiar. If I go back to Linrad, I have this peak and I have these humps here, but I'm running my oscillator from an unfiltered power supply. I will look at what the signal is when I run it directly into the test system. This is the signal I was sending into my multi-crystal unit, and you can see it is very noisy at 500 Hertz, minus 156, and there is no balancing of the parallel capacitance of the crystals, so the signal goes through with some attenuation but not terribly much. And at 10 Hertz I can read minus 140. And I should see the same here. 10 Hertz minus 140. And then at far offsets minus 158. I will add an RC filter on the power supply. I have added a low pass filter now, and you can see in the baseband waterfall all these spurs are gone now. And I haven't reset. I will do that. It is an 8 ohm resistor here, directly on the power supply. About 1.7 farads, 80 times 22,000, 25 volts, and just in front of the oscillator, my old channel 1 oscillator. Here is the phase noise now when the power supply is filtered, and here without the filtering, and this noise is gone, and this, so it is much cleaner, but the noise level is not much lower, and particularly here it is degraded by 10 decibels at 0.1 Hertz. So there is a stability issue somewhere. And in Linrad I can see that the wide noise goes towards minus 160. At this point minus 158. And I can see at 30 Hertz, that's here, it looks like minus 149. And 20, 30, minus 149. So Linrad and PM2060 agree on the noise levels of the phase noise. Here is what I see when I send the signal with the DC supply filtered. This signal, sending it through my selective multi-crystal amplifier. And what I see here is a little bit more than 6 decibels. It could be the filter response. It means that there is a contribution from the input signal, maybe from the PM2060, and maybe from the amplifier or the crystal. So this is really hard to say anything about, but at, let's say, 30 Hertz here, the filter has suppressed enough. So this must be from the crystal filter or from the amplifier. And the same here, probably, because, well, here I am in the flat region, and I can see from here I have minus 158, and here I had minus 182, and that is 24 decibels. And at 100 Hertz I'm already in the flat region, so this difference is much less than 24 decibels. So it means that what I see here comes from amplifiers or crystals in my selective amplifier. I have added a crystal filter between my channel 1 oscillator and the multi-crystal unit that I am testing. The filter adds significant amounts of noise. At 10 Hertz now I have minus 128, and that's, 15 decibels or something, a degradation. But well above the corner frequency, then it doesn't add any noise anymore. So at 10 kilohertz, I see minus 187 here. And at 100 kilohertz, minus 190. I have added a second amplifier stage here, first with a step-up transformer, increasing the voltage by a factor 2.5. It's a T50 of material 2. Then the amplifier has a bifilar winding to make the gain 1, but to give more power. And it's 2 J310 in parallel to get the desired output into a 100 ohm load on the sources. That's a 47 ohms resistor, and then the output, which then has an output impedance near 50 ohms, because the impedance on the sources is very low in this configuration. The first stage has 2 J110 in parallel. That was when I took the output from the sources to get a low enough impedance to do measurements with it. And I have left the 2 in parallel in place. It makes the impedance lower at the basis of the J310, and that could affect the noise by this transistor a little. The input is 18 milliwatts, and I have tuned then for 0 in imaginary part of on the resonance, and for 50 ohms for the real part tunes here, and this sets the frequency together with this capacitor, which no longer is 220 pf, because I have gone up a little bit and removed the extra 20 pf I had to add before. The output is 38 milliwatts, 16 dBm. I want to evaluate the flat noise floor far from the carrier. To that end, I will use a crystal filter made like this from 10.7 MHz crystal. I had in my junk box from old crystal filters with a bandwidth of 30 kHz. They were since the time when they swapped from 30 kHz bandwidth in the commercial world to 15 kHz, I think it was. I have them to resonate on the same frequency by series tuning the collection of 10 with a single capacitor. This tunable inductor is to make them resonate at 10.0 MHz, which will stop the transmission of the carrier into the LNA preceding the Perceps receiver that I'm using to evaluate the noise floor in this point at 10.7 MHz. With this system, when I set this stepped attenuator to 0, I get 18 milliwatts, which is the rated input of my device under test. The output power then is pretty high, so I have to set a lot of attenuation here to not overload my test system with the PN2060 and my direct conversion receiver with Linrad. So this hybrid is in front of these attenuators, so any noise here is not going to degrade the performance of the test system. The value reported by the PN2060 above 100 kHz here is about minus 187, and it's noisy, as you can see, but I can see the imaginary part is well below. But specification says better than minus 170 up here, so this is not really trustworthy, and I want to try to see what the real value might be. Here is what I see in Linrad. The signal at 10.7005 MHz is, according to the S-meter, minus 167.12 dB per hertz. And if I disconnect my device under test, remove the supply voltage from it, on the contrary, there is a dip in the noise close to the frequency where the maximum was. This is because without any supply voltage, the junction FETs are resistors from source to drain, and that way the output can look into the impedance of the crystals, and the lower impedance affects the LNA. So I go back with the full operating voltage. The signal level is maximum, which I can see here. Well, I have to restart the PN2060 that is failed. But I can read the signal level. It says 9.5 dBm, and that is the normal signal level that I'm using here in the system. The channel attenuators are set to 15 dB, which means I can reduce the carrier with 15 decibels and set these to 0 and make a measurement where the flat noise floor should be 15 decibels higher. 15 decibels of attenuation here and 0 attenuation here. It does not take much time to see where the noise is. Minus 172 according to the numbers here, and they agree well with the flat line. So minus 172 and 15 decibels below that gives me minus 187 dBc per hertz, in line with what I saw measuring at full power with the PN2060 but then the measurement was very noisy and it took a long time. Now with a 15 decibel lower carrier, I can evaluate where the noise floor in 10.7 megahertz is. It is minus 167.27. That differs by 0.1 dB from the noise floor at full power. And I'm not so sure that it's relevant. So the noise does not change when I put the carrier on or off. I have removed the carrier, means I set the attenuator to minus 120 decibels below normal power. And then I connected the LNA directly to the output of the device under test. And then I see a noise floor which is significantly higher than what I had through the filter. It is higher by about 3 decibels. Now I can measure in a much wider bandwidth since the narrow filter is no longer involved. So I read out what I have here. This is the noise power out from my device under test. And here I have connected my noise head instead and set it to a suitable noise figure. Here it is set to 7 dB. What I can see with perceives is the same level as I had before, within 0.2 decibels or so. When the noise figure meter indicates 0 dB, it means that the temperature coming out from the noise head is 3 decibels above room temperature, because the instrument is calibrated assuming that the noise level is doubled in the test system. And here is what I found. Noise figure meter shows 7 decibels, and that means that the noise temperature it delivers is 10 decibels above room temperature, and that is minus 164 dBm per hertz. And with the carrier at 16 decibels, it means I have minus 180 dBc per hertz for the total noise, amplitude and phase noise. So I find minus 183 dBc per hertz for the phase noise, the single sideband phase noise, and I measure with the PN2060 minus 187. So there is an error of 4 decibels. So I'm doing something wrong, it seems. I look at the output impedance. It says 61 ohms and 4 ohms inductive. So I should change that 47 resistor to a 36 ohm resistor instead. Now I have replaced the 47 ohm resistor with a 36 ohm resistor in series with 3.3 nanofarads. And this gives me 49.5 ohm and almost no reactive components. Correcting the output impedance made no difference in the phase noise measurement with the PN2060. It gives me minus 171.8 or minus 172.4. And it's hard to see here what the noise is with the decimal. I can magnify and use a pixel editor. So here, that is minus 170. It has a coordinate of 241. And minus 180 is at 395. And the mouse cross is now at the representative place here. And there the coordinate is 275. This gives me 0.22 decibels. And I can see here that the red marking is a little bit high. the marker is set on a single pixel. It's not a smooth curve that is set to give the marker value. I think maybe this will be changed in the future software releases. The smaller resistor in series with the output has made the available power to a 50 ohm load a little bit higher. Now I see 4.60 volts in the 50 ohm of the oscilloscope, peak to peak. I attenuate by 60 decibels here. And as expected, the signal is 1000 times weaker. I moved the cable from the oscilloscope to the perceivs, including the low noise amplifier in front of it. And here is the signal. It is not strong enough to saturate. And I don't want to hear it anymore. I calibrate the S-meter in the dB per hertz mode to show -60. Now it's calibrated and I can read -60 decibels for the carrier here. And then I can look at the noise floor. It comes here. -182.62. That means that the phase noise is -185.6 dBc per hertz. And the noise floor is -182.7 dBm per hertz. But this isn't really accurate because the noise figure of my LNA is not terribly good. Here I have connected the noise head of my noise figure meter, which is perfectly 50 ohms, exactly as my device under test is now. And that changed the noise floor from -182.7 to -187.8. That is 5 decibels. So there is a contribution from the system noise for the perceivs. So I measure this noise figure. This is pretty close, from 187.8 to 184.96. That's nearly 3 decibels. And that is for a noise figure of 4 decibels. The direct measurement with the perceivs gave me phase noise -185.7 dBc per hertz. But this measurement suffers from inadequate signal-to-noise ratio. Signal, that is the noise of my device under test, and noise is the noise of the perceive system itself. So the ratio S plus N divided by N in decibels is this minus that. That's only 5.1 decibel, which means it is a ratio of 3.24 times. So if I subtract the noise, then I get the ratio to 2.24 times. That is 3.5 dB. So the phase noise I arrive at, -185, has to be corrected, subtracting the difference between these two. And that gives me -187.3, which is very close to the second measurement after I adjusted the impedance with the PN2060. So my measurement establishing the noise floor with the noise figure meter that gave an error of 4 decibels, I must have made a mistake, thinking upside down somehow. If you know what the error is, please tell me in the comments below. I decided I want to evaluate things around the crystal, and then I suddenly found that with some loads on the output, if the load here is not resistive on all frequencies, there could be oscillations. I found at about 80 megahertz. To stop that, I put a capacitor to ground from this point. And that helped, and it increased the gain significantly. So I had to do various other changes. And I also found oscillations at several hundred megahertz that were very unstable and would change if I moved my hand around these components. That helped to put 47 ohms and 12 pf to ground here. That doesn't affect what happens at 10 megahertz. And the higher power required one more J310 in parallel and a change of this resistor. And now the output power is much higher. It is 92 milliwatts. It was 38 milliwatts before. So it is more than 3 decibels more signal now. But I want to continue to see where are other problems with this design. I have disconnected the second stage, and now I measure the impedance on the crystals and find that that is about 760 ohms. When I connect the second stage, the impedance magnitude becomes much higher, 1.2 kilo ohms, and the frequency about 2 hertz lower. When I look at transmission on the source follower output, I then find the Q 1.044 million, and loss is minus 4 dB. When I connect the second stage, things become a bit different. The Q is now 1.3 million, and the loss is minus 3 dB, and the frequency is a little bit lower. So what is here is I have unintended feedback. The output from the second stage couples to the input of the crystals. That's because of bad layout. And this is how it looks. Certainly a bad layout. But I can do experiments with it to decide what I want to do next. Here is the input impedance of the second stage. It is not as expected. It is highly capacitive, 200 pf. Here is the transmission through the entire box, and it says 1.03 for Q. I had applied an inductor, 820 nanohenry, to balance the capacitive input on the transformer. And I remove that inductor, and then I get the feedback. So Q this time is 1.8 million. So feedback is even stronger. Well, it is critical when I move components a little bit, I guess. So I put that inductor to balance the reactive component at the input of the second stage, and that shifts the phase of the feedback probably in order to not affect the performance of the filter. I don't know what this means for noise properties and other things. A little bit interesting. I'm using the crystals in a Q multiplier configuration, and then all of it in an oscillator. I don't think this is an advantage. Here is what I see when I have an inductor of 820 microhenry across the primary winding on the transformer between the stages. Well, part of the second stage. And this is not good at all. The input that I'm sending into the unit is like this. and you look at 1 hertz here, there is a degradation of 5 decibels. And this is a very nice straight line that has some cause. And it looks like f minus 3 for 1 decade. It goes from here, 1, 2, 3. So it's 30 decibels per decade and over a wide range. And this is a new phenomenon that I haven't seen before. So I will remove that inductor to see if it is back at normal performance again. Here is the signal I'm sending into the unit, and this is what comes out from it. And you can see at 1 hertz, this is what I'm sending in, and this is what comes out. So there is something that generates noise at 1 hertz. At 10 hertz, the filter bandwidth makes the noise, this noise, a little bit lower, but not enough. So there is a noise contribution here as well. And I don't know exactly. This seems to be for normal, what I have had when it was working well, minus 170 at 100 hertz. I have reduced the signal level by 15 decibels. And here is what I see. And the signal I'm sending into the unit is this. So this flat noise floor is degraded by 15 decibels. And then what comes through is about 30 decibels attenuated by the crystal filter. Since there is no balancing of the parallel capacitance, this is expected. But here at 100 hertz, the attenuation by the crystal filter is probably similar. And this moves nearly the same as here. So this could be the noise from the input signal that comes at this level. But here is clearly noise generated by the unit under test, and here the signal is degraded, here where the filter is flat. And I don't know exactly what to think about this, but what is really unexpected is what happens when I compare with the signal at full power. Here is what I found running at full power. And the interesting thing is here. 15 decibel reduced has improved the noise significantly. That means that the noise I see at full power is phase modulation produced by the crystals or by the amplifier. It could be that at this higher signal level, the amplifier causes small changes of the capacitance that loads the crystals and thereby shifts the frequency a little bit. Then it should be the same here. And if I compare with the signal I'm sending in, it is lifted by about these 5 decibels, as I see here. But lowering the signal level by 15 dB does not change the amount of phase modulation that is being added at 1 hertz offset. The whole thing is well, interesting, and I don't understand what's going on. Here is what I see when the signal is attenuated by 5 decibels only. And I compare with what I saw when the attenuation was 15 decibels. And the difference here is obvious and well understood. And it stretches all the way here, although not so strong. But here the result looks exactly the same. And here. And here. And it's a difference of 10 decibels in signal amplitude. So it means that what I see here, well, I have to compare it with what I send into the unit first. So here is what I have, and in this region, independently of the power level, 5 decibels or 15 decibels below nominal. And here is what I send into the box, and at 10 Hertz there is an attenuation of maybe 7 decibels, maybe 8. That could be the attenuation that the crystal filter provides. But here there is clearly an added noise of about 4 decibels. And that is independent of the power level, so I assume it's a varying reactive component seen by the crystals, or maybe something by the crystals themselves. I will do some other experiments to see if I can find ways to not add noise at 1 Hertz. I have scrapped the second amplifier and made something completely different. First there is a step-up transformer, a factor 2.5, and then a source follower, and then the output. This gives me 20 milliwatts of power. This is very prone to self-oscillations. I had to put ferrite beads here and here and here. And yet it might oscillate at some particular levels or load impedances. So I will have to check the impedance into this transformer and into that transformer to make sure the thing is stable. Performance is interesting. Here is what I see with full power input, and I will compare it with the input signal, which is this. And I go back again. You can see the level here is similar, but there is a hump, and performance at 1 Hertz is bad. It's only 114. But here is what it looks like when I have reduced the level by 5 decibels. And this is much more interesting. If I compare with the input, you can see it is the same here. Well, it is minus 6 decibels, this. And then I made an experiment at minus 10 decibels also. It's this. And I haven't set it properly on screen, I see. Again, what I'm sending into the unit. Look here. And what I have now at minus 10 dB. It looks like there is no added noise here. And here, questionable. And here I can see action of the filter. And what happens here, I don't know. I will change the layout and connect suitable components here to make the impedance that the base is seeing nice resistive over the VHF range. And the same thing for this transformer. And then I hope it will not be an oscillator at 100 or many hundred megahertz. That will be a new video. This one is long enough already. The instabilities that I suspect come from oscillations behave like you can see in this slow motion video. Look around here. And then it drops down slowly. There is one event. When I look at the carrier frequency without any signal applied to the box, this is what I see. And here you can see the thermal noise of the crystal. At the resonance frequency the impedance is high, so there is a lot of thermal noise. And then when I go away from it, there is less because the impedance is lower. And at some point the flat noise of the amplifiers wins. So on the peak I have a reading of minus 73.366, and I click outside fairly close because there is an undulation here due to the software in the, or rather the firmware in the perceives. There are digital filters in there. But I wait for a while and then I can read out the noise at, is it 100 Hertz above. The separation between these peaks is 2.5 kilohertz. So I'm within the flat region here. So I measure a new value for the new noise level I found here at this point. And I see 86.65 if I read dB per hertz, and the previous was 73.36. So the difference is 12.3 decibels. And of course I could look at the screen and say, well, here the noise floor is at 34 and the noise peak is at 47. And that's 13 decibels. And I can see the noise is a little bit higher here. I was too close. Anyway, say 12.5 dB. What you just saw was the old configuration. Now the impedance on the gates of the FET is higher. So I can see here 29 and here 44. So from 12.5 to 15 is a really small difference. I had expected more, but this is because I have only one amplifier stage. I have connected a dummy load to the perceives, and you can see the noise is the same as what I have from the box. So some low noise amplification should make this noise peak a bit stronger, I think. And that would improve the sideband noise at wide separations.